Okay, good. Whoops. Okay, well that was a very, I feel bad having to follow that act. Oh, having to follow Kate Calvin and stuff. Um, so I'd like to start by first thanking the IAMC organizing committee in Nice for a great conference. This has been really great for me to attend, even though I've been half asleep, I feel like, with the jet lag for most of it. But I've met a lot of people doing similar work. I found myself surprised that there's so many people doing stuff similar to me. So this has been really great. I really appreciate such a great conference put together. I think this is my second time coming to the IAMC conference. The first, I want to say, was one of the first ones, and the room was much smaller than this. There weren't that many people. So again, kudos to the IAMC leadership for bringing together such a great community. John has been telling me this, because we work closely together for a long time, that this community has really come together, and it's really clear from just looking out here, and I know a lot of people had to leave. It's just great to see. So congratulations to John and the other IAMC leadership for putting together such a great community. So what I want to present today, I guess I only have about, 15 or 20 minutes, I think, right? Okay. Is kind of two parts to this presentation. It's joint with John Wyant, right here, sitting here. And the first part is going to be some material from a paper that we're writing for the annual review for resource economics. And so we're at a stage that it'd be good to get feedback. And so I thought it's on the evolution of integrated assessment. It's supposed to come out. We have a draft that's at annual reviews right now. It's supposed to come out next year. So any feedback on this work, I thought this would be a great, selfishly, so a good opportunity to kind of present it to this group and get any feedback on that. And then that will segue into an overview of our project where we're developing the next generation, we think, of use-inspired tools. Okay. So in terms of context, kind of going back to the beginning, and I feel like everyone in this room knows all of this stuff, but so the evolution. So integrated assessment in the climate change context, and we're very careful in this paper of pointing out that integrated assessment was going on before climate change, before Nordhaus, in acid rain and other environmental issues. But in the climate change context, it began with the pioneering work of Bill Nordhaus. We all know that. We were very happy that he won the Nobel Prize just a year ago. I think it's been good for business, for a number of people. And these earlier IA studies were focused on, in general, I will say, on long-run global mitigation policy analysis. And as a result, a lot of these IAMs are very coarse in spatial, sectoral, and temporal scale. And so on the right here is from the IPCC Second Assessment Report. It's actually the chapter that John led, which shows this end-to-end. This was kind of the wiring diagram to depict integrated assessment at the very beginning. So it's this end-to-end wiring diagram where you see kind of in the dotted boxes would be reduced form representations of kind of an emissions, like a socioeconomic model that would give you emissions, feed into an atmospheric chemistry model, feeds into a climate model, and then feeds into different kind of sectoral impacts models. Rarely, but sometimes it would come back to the emissions model, but at this early stage, it really kind of ended at that point. That gave rise to two types of integrated assessment models, we feel. And some of this is from, a lot of people have written about this already. But the first category being what we're calling, it's great to be in this community because I've heard these terms being used by people the last couple of days. So it seems like it's something that's already been adopted by this community. But the benefit cost, kind of differentiating between a benefit cost IAM, which is the DICE model. So you see down here on the left-hand side, that it's, again, reduced representations of these different components, but a lot of arrows going back and forth. So the whole point was that there were going to be feedbacks from all these different component models. These benefit cost IAMs are really focused on determining, in the early years with the DICE model, determining the optimal level of emissions reduction, so trading off abatement costs with damages to get the optimal level. More recently, now there's a huge literature and a huge community of people doing social cost of carbon work. So, what's the increase in damages from a 1-unit change in carbon? So there's a whole kind of industry now on that. That is different from the detailed process IAMs, which is something that I was really more involved in for years, where you have, it's really, these models are used to, have been used to generate these emission scenarios that are used as inputs to the Earth system models, and it's really just kind of the focusing on the human activities and socioeconomic model with a lot of detail to get that type of emissions trajectories that we're looking for. So the next generation of IAMs, and not to say that those have left us, we're just building on kind of these IAMs that are already in existence. So, and again, this is a general statement, but the lack of serious mitigation efforts at the global scale, and this is kind of from a U.S. perspective. The modeling focus has moved from kind of, not that we're not doing mitigation policy assessments, we certainly are. We can see from the last couple of days we have a lot of good work going on there. But we're expanding beyond mitigation policy assessments to understanding impacts. And that's why we saw this whole session on impacts was excellent, by the way. I sat through all 3 of them, and it was really, really great. So we see a lot of people now really using IAMs to do impact analysis. So the Impacts Adaptation and Vulnerability Committee, you can think of that as kind of working group 2, the IPCC, has become interested in the use of IAMs due to the emphasis on interconnected systems. So it's something that, we're natural growth of the use of IAMs. And that's not to say that, the image model and other models did do impacts work early on, so we don't want to, ignore that. But usually these earlier studies were at a much coarser resolution and usually didn't assign economic value to those impacts. Importantly, and you can see this with a lot, and this is still the case, is that there's a lot of really good econometric, statistical studies and process model IAV studies that are out there, but they're very specific on sectors and region and ignore kind of the interactions. And sitting in on the impact session this week, I feel like we all recognize that, and we're all trying to do that now, which has been great to see. So I'm not the only one that has seen that. But historically, there's really been this disconnect between these detailed empirical, and what I mean by kind of these statistical and process model impact studies and IAMs. So what we want to see, and what we're seeing in the literature, is this movement away from this early years of this end-to-end depiction of integrated assessment to something we're seeing in the National Climate Assessment, which is a network, where everything is very detailed. You have everything connecting to everything. That's where we'd like to be. We're not there. But that's going to require some work, and it seems like the people in this room are already on the case of trying to get there. So the useful, and I think so use case framing rather than focusing on specific sectors or regions. So this focus has shifted to developing generalizable frameworks for specific types of problems. So no longer studying what's the impacts of water scarcity on ag, but rather we want to study the impacts from competing demands for scarce water, which would include ag and other uses of water that are competing with each other. So this new emphasis requires tools that capture detailed sectoral and regional interactions. So that's really the emphasis of this program. So I just kind of want to show you in terms of comparison of kind of definitionally what we see. So if you look, this is from the Integrated Assessment Society. If you look at the definition of integrated assessment, you see words like problem solving, decision making, public policy, very prescriptive, kind of motivation for this type of work. If you look at the definition of multi-sector dynamics, this is from the U.S. Department of Energy, you don't see those words. You see words like advanced scientific understanding of the complex interactions, interdependencies, and co-evolutionary pathways, blah, 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 for critical infrastructure, that type of thing. So you can see kind of this difference in emphasis. So that leads me to our project. So on top of DOE kind of moving from the term integrated assessment to multi-sector dynamics and an emphasis more on the impact side, they've moved away in terms of their funding model from funding individual people, like kind of letting all the flowers bloom type of approach to rather funding a couple big teams. And thankfully, John and I have been a recipient of being one of those big teams that they're funding at a high level. And it's called the Program on Coupled Human and Earth Systems. We affectionately refer to it as PEACHES. You can see that nice little logo down there. And I'm taking credit for that one. So I had to talk John into that. So there's a little history there. So it's a $20 million 5-year cooperative research agreement with the Department of Energy's Office of Science, this new multi-sector dynamics program. The motivation stems from kind of the recognition that energy, water, and land systems interact in complex and, as many of us know, poorly understood ways, yet it's really important for things we care about, like international trade, food security, critical infrastructure. So what our program is trying to do is to create new state-of-the-art integrated modeling frameworks to advance the quantitative understanding of these coupled systems. Okay? As you can imagine, with a large grant like this, we have a lot of people involved. We have about 10 institutions, about 20 investigators, lots of postdocs, and lots of grad students from many disciplines. And this is kind of a subset of the disciplines that are on our team. And I'd like to show, at least this is, if you go to our website, it has everybody, all of our postdocs and grad students are listed there as well. But this is just a picture of the senior personnel. And I bring this up for a couple reasons. First of all, so that you can see kind of the range of disciplines that are being represented in the project. You can also see a lot of really big names and people who are really top in their field that are part of this. And what's unique about our project is that every person here publishes well. Every person here is top in their field. Yet they want to do something beyond just doing well in their own discipline. So every single one of them are working on these transdisciplinary, multidisciplinary, whatever term you want to call it, working together to solve these. So you have Tom Hurdle working with Ryan Shriver, working with Wolfram Schlenker, so we had these teams of people that are working together on the problems. It's no longer the case, and DOE would not be funding us if this was the case, if people were just doing their little piece of it and throwing it over the fence. That is no good anymore. Okay, so anyway, it's a unique individual to find somebody who wants to get involved in that type of thing, but everyone's interested in it. They think it's a really interesting problem. And they like learning about other kind of disciplinary approaches and models, so it's worked out really well. So a little bit more about PEACHES and what's really behind this. So it comprises 4 main research program elements. This first program element is really the core of the project. So we're developing alternative integrated energy, water, land modeling frameworks. And they differ, so we have 1.1, 1.2, 1.3. They differ primarily on spatial scale. So we have one that's at the grid cell level. We have one that's kind of at a sub-regional level because we're looking at governance issues, so you're looking at kind of state-level issues. And then you have one at the global level. And what we convinced DOE is that we need kind of 3 different projects working at issues at different scales so that we can compare and contrast approaches. If you're doing it at the grid cell level, what are you trading off? What kind of trade-offs do you face versus something that is at the global scale? So we have, and I'll bring up that work in a minute. Program element 2 kind of seems like a throwaway line there, but actually it's turning out to be one of the more important parts of this project, which is if you're talking about coupling different component models in a true integrated way, then you need to do something on the computational side. So you need to have innovation on these integration methods, so translational tools and coupling software. And that's something that, all of us are computational people, but we're not computer scientists. Some of us think, I have a computer science undergrad, but, I think I know it all, but it's obviously I don't. We're having all sorts of problems sometimes solving this stuff on high-performance computing, and so we got to get some innovation on that side. Program element 3 is looking at issues that cross-cut all of this, which is uncertainty quantification and model diagnostics. Got one of the top people right here, and building a community of practice, hopefully similar to this. So, what do I mean by integrated model? What are we really doing here? So I just thought I would use a quick example research question of what is the impact of water scarcity on the interconnected energy water land system. So usually in the past what we've done is we say, especially if you think about the econometric work that's being done, you take information from the Earth system model and you estimate that on crop yields, and you get kind of, well, if temperatures go up by this much, then we'll have a fall in yields of that much. We'll apply a crop price to it, and that's our impacts. That's typically what we've done in the past. What's missing from that? Well, what's missing is the fact that if farmers will respond to that, maybe they'll start to irrigate more, maybe they'll move from rain-fed crops to irrigated crops. So then you need to know something about the hydrologic system and kind of, does it have the water supply to be able to deal with that increased water demand? So what else are we missing? We're also missing the fact that you have competing demands for water from the urban sector, from the electric power system that needs water for thermal cooling and hydro. And so you need to know about something about who's going to get that water. Okay, so the water rights system and the allocation of that water is important. In the West, okay, thank you. In the West, a lot of those water rights end up in the agricultural system, so they're usually the ones who get the water rights in the West. If you're interested, I can talk to you more about that. And so does that mean the agricultural system is not impacted by water scarcity? No, because the fact that these other sectors are not getting the water, there's going to be a kind of economic impacts, right? There's going to be a impact on productivity, which is going to affect prices that feed back into the agricultural system. So indirectly, even though if ag gets all the water, they're going to be indirectly impacted by water scarcity through this mechanism of competing demands for water. Okay, so just a little bit about each one of these three. Based on that. So this is looking at problems at the grid cell level. And it's led by Tom Hurdle with a team of people. And they're looking at issues at very fine scale. And if you're looking at fine scale issues, then you're going to have to trade off kind of the detail on the socioeconomic side, and maybe you're not hard coupling, maybe you're having to pass things through soft coupling. And they're looking at issues, this is just an example of one research question they're looking at. What if states adopt biomass co-firing of coal units to meet renewable portfolio standards? So if you're going to do that, you need to know kind of spatially where things are located. Where are the coal units you're talking about? Where are they in relation to where the crops are, the biomass crops are being produced? And what kind of impact does it have on water quality? So where are the river basins in that? The project that I'm leading in my team is really the example I just showed you. So we're looking at issues of how do water rights affect the allocation of water and the competing demands for water. So this is just a quick example. We're building water rights into the water balance model so that you can say, this is a complex graph, but essentially say, if this is how much water we have, this is who's going to get it. So we can actually look at the economic impact